Okay, hi there. This is Daryl Worthy. So I am doing a Camtasia lecture now because we can't meet because of the coronavirus. And so this is for my psychology class 671. We're starting the second half of the course today after it covers mainly regression, but also other research methods topics related to that. And so we ended before spring break talking about the assumptions of regression. So we finished most of those. You can view the PowerPoints if you need to, but I'm going to go ahead and move on to categorical predictors. And so this will be kind of the first material that the final exam, or we might do a final project. That was something we got emailed about yesterday. So I'll let you know, what the status will be. But for now, expect to have a final exam on categorical predictors. Then we'll talk about interactions in several different lectures. And then we'll also talk about mediation, and then logistic regression, and then a little bit of multi-level modeling at the end. So this really caps off our graduate student first year stats track, two course track in psychology. So it should be kind of the most advanced material. But of course, there's much more advanced material and courses you should take after this. So I'm going to go through this. Just as these lectures will be recorded or posted on YouTube, so it's possible, people outside of the class might view these and find them helpful. I want to give an acknowledgement to the person who taught the course before I started teaching this in fall of 2012, Dr. Aaron Taylor. He came up with a lot of these, or he developed a lot of these slides originally and then gave them to me. And then I've modified them over the years. So I want to acknowledge his work since these will be publicly available on YouTube. And so Dr. Aaron Taylor has contributed a lot to these slides. So if you like them, it wasn't just my work, it was also his. Okay, so let's go ahead and get started on categorical predictors. So mainly this is all just kind of setting us up for using categorical predictors in interaction. So for example, we can have an independent variable that is categorical, and then we could see if it interacts with a continuous variable. So for example, maybe you find a correlation between one continuous variable and your dependent variable in one condition, but say not in others. So that might be where you want to test an interaction. So but for now, we're going to start with how we treat categorical predictors in regression because they're a little bit different than how we treat continuous valued variables. Okay, so let's start with an easy example. Say we wanted to use sex as a predictor, and we only included participants who reported being either male or female. Okay, so it's only two values. It's dichotomous. So a code, if we're going to code for a dichotomous predictor, it just has to meet these two or these criteria. Okay, so participants in the same group, so if they have the same sex, they would have the same code score. Okay, and then participants in different groups have different code scores. So that is pretty much it. Okay, so let's see, why did that do that? Okay. So those are our only two criteria. So some possible codes might be we could code based on U.S. life expectancy. So if a person was a woman, we would give a code for the dummy code of 80.7. Or if they were a man, we would give a code of 75.4. At least these were The average life expectancy is a few years ago. Who knows what coronavirus will do to that. We could also give codes based on the mean digit ratio between your your index finger and your ring finger. So if you hold your hand up in front of you and hold your fingers like straight up, I'm a man, so my index finger is a little bit shorter than my ring finger, and for women it's usually closer to being equal. We could code based on that. So if we did that, we would give 1 if a participant was a woman, and 0.96 if they were a man. We could also code based on mean height. Okay, so men are a little bit taller. This is in meters. We could do it in centimeters. We could do it in feet. We could do it in yards. It wouldn't matter. Men are a little bit taller on average, so they would get a code of 1.763. Women would get a code of 1.622. Or we could just pick some arbitrary numbers. So women get 44.217. Men get negative 129.151. Okay, so any of these would be fine because they satisfy those two simple criteria. But they're not really ideal. So there is a better coding scheme. If we used those criteria, then any old coding scheme we picked, as long as it was the same for everyone in one category and a different number was used for everyone in the other category, it would be fine. And we would get the same R-squared and p-value, so the same kind of model fit essentially. But what if there was a coding scheme that also made B0 and B1, our coefficients, more meaningful? Okay. Unfortunately, it's called dummy coding. So, at this point in class, I would ask you to raise your hand if you've heard of dummy coding. Hopefully a lot of you have already heard of it. It's really simple. Okay. So to make a dummy code, assign everyone in one group a 0. Okay, so say you could assign all males as 0 or all females as 0, and then assign everyone in the other group a 1. Okay, so very simple and straightforward. So that's it. So you can read more about it in this book, Dummy Coding for Dummies. Obviously this isn't a real book, but if it is, it would be pretty short because there's really not much to it. Okay, so the only decision to make in dummy coding is which group to assign which value. So the group assigned 0 is called the reference group. Okay, so often the reference group might be the larger group. Perhaps it's the group we're kind of using as like the comparison. Maybe it's our control group, and then the other group is the experimental group. It really doesn't matter. It just matters that you convey to readers of your excellent, journal articles which group is coded as which. Okay, so say if we were studying firefighters and coding sex, men might be the reference group because there are more male firefighters. Okay, but that's just one heuristic. Again, it's not really a statistical question. It's kind of just something that needs to be declared and stated so readers are clear on what you're doing. So then, you choose the reference group that makes the most sense to you. Okay, so dummy coding gives our intercept B0 and then our slope coefficient meaningful and useful interpretations. So B0 is the predicted score when the predictor is 0. Okay, so the predictor is 0 for the reference group. So we coded, the reference group is 0. Therefore, the predicted score for the reference group is B0. Okay, so we look at the intercept, we see what its value is, and then we can tell, okay, that value is what we would predict as the mean value on the dependent variable for the reference group. Okay, so because we have no other predictors in the model, the predicted score for a group is its mean. Okay, so B0 is the reference group's mean on the dependent variable. Okay, so it's really as simple as that. So what's nice is hopefully you can really understand this, and that way you can really start to be able to easily interpret what these regression coefficients mean. So you run a regression, you see what the intercept value is, you know what you coded as the reference group, and so you know, oh, okay, that's the mean for the reference group. You can then go and cross-check that when you say compute the reference mean by some other means like Excel or something like that, that you get the same value as this coefficient. So you should get that same value for the group's mean either from this regression or from another way that you would calculate the mean for a group. Okay, so then the other slope coefficient, B1, is the change in predicted score for a 1-unit increase in the predictor. So this is the same as we've been talking about for continuous regression. Okay, so the groups are scored 0 and 1 on the predictor. So B1 is the difference in predicted scores for the two groups. Okay, so because we have no other predictors in the model, the predicted score for a group is just its mean. Okay, so B1 then is the difference between the groups' mean on the dependent variable. Okay, so from B0 we know that that's the mean for the reference group, and then B1 tells us how much higher the mean for the group coded as 1 is, or lower, compared to the reference group's mean. So if B1 is positive, then if B1's positive, then group 1 has a higher mean, or larger mean than group 2. If B1 is negative, then the group coded as 1 has a smaller or lesser mean than group 2. Okay. Okay, so say we're interested, say for an example, we're interested in whether men or women are better at mental rotation. So these are the types of tasks that you might do in a mental rotation task. So you're given this, and then you're asked, are the two objects the same or different? So if I was teaching in class right now, I might say, okay, raise your hand if you think they're the same. Raise your hand if you think they're different. Hopefully more of you would raise your hand to say they're the same, because they are the same. So if you know I rotated this one to where it's in the same position as this piece right here, we would see that they are the same. Okay, so these are the types of mental rotation tasks. It's like a classic kind of cognitive task. Okay, so how about this one? Are the two objects the same or different? Okay, what do you think? So hopefully they're, you can see that they're the same. So if I rotated this kind of like that, you can't really do it, but if you think about it long enough, you'll see that they are the same. Okay, how about these? Are they the same or different? Yeah, so if you said that they're different, you are correct. So these are different. So if you kind of tried to rotate them, you would see that they're not in the exact spot. Okay, so you couldn't get them to be rotated to where they are the same. They're actually different objects. So that's a mental rotation task. So say we scored these. So there is a classic finding where one group, men or women, are better than the other. I'm not going to tell you what it is, but you can go out and look. There has been a little bit of controversy, but this has been something that's been studied for like 50 or 60 years. So we could pretend these mean scores are either accuracy scores. In that case, say men would be more accurate than women. Or we could pretend that they are response time scores, so average response time maybe, and maybe women scored or responded quicker than men, meaning like they're better at this. So you can go out and Google mental rotation, sex differences, and you'll find all sorts of papers on this on Google Scholar. So if you want to find the correct answer, and of course if you think that the research that's been done is wrong, you could do your own research and disprove that or whatever. Okay, so we'll use these as our dependent variables. So the difference is 19.6. Okay, so here is our result. So this was actually done in SAS. I don't use SAS anymore, but these would be what you look like. You can find kind of the same info here. Here's the p-value. Okay, so p equals 0.015. So significant at the 0.05 threshold. We have a low sample size, obviously, only 10 participants in each condition. We would want to run a much larger study if this were a real study. There's our R squared. So just our predictor of sex accounts for about 28.6% of the variance in mental rotation scores. So that's a good amount. Okay, and then this is our coefficient down here. We only have one predictor in the model, so just like with a continuous regression, it gives the same p-value as the overall model because we just have one predictor. Okay, so same values as for other coding schemes. So B naught is the mean for the reference group. Okay, so the mean for the reference group is 59.2. Okay, if we go back, let's go back a slide real quick. We can see that that is the mean that we computed just how we would normally compute a mean by summing all the scores and dividing by the number. We get 59.2. And so it's good that we can check and verify that we get that same value for the value for the intercept. Okay, and then we also computed our difference on the last slide. So our difference was 19.6. Okay, and so that is the coefficient for the slope. Okay, so the difference between the two means, so males are score 19.6 higher on this dependent variable than females. Okay, so that's what that coefficient tells us. Now, so that was with females coded as 0, males coded as 1. Now, what if we coded males as 0, females as 1? Again, it doesn't matter statistically. We get the same p-value up here, okay, and down here as well. Same R squared value, okay, but now we get different coefficient values. Okay, and so now B naught is the mean for the reference group, so the mean for males. And then B1 is a difference between the comparison group, so here females, minus their mean minus the male means. It's lower by 19.6 units, so it's negative 19.6. Okay, so it's symmetrical, it's the same absolute value, but it's just different depending on whether you're coding one group as the reference group. In this case, it's males. On the previous slide, females were the reference group. Okay, so say if we were to do a scatter plot. So we've been doing the scatter plots a lot for continuous variables. We could do that for a dichotomous variable. It just looks a little bit different. So here we're dummy coding now with females as 0, the reference group, and males as 1, the comparison group. Okay, and so they're all going to be on the x-axis at either 0 for females or 1 for males. And then on the y-axis we plot their different dependent variable scores. Okay, so here women have a mean of 59.2, men have a mean of 78.8. There's our slope coefficient, so we have a 1 unit change in x going from 0 to 1 on the dummy code, and that translates to a 19.6 unit change in y. Okay, so here is our predicted regression equation. So predicted rotation score equals 59.2 plus 19.6 times the dummy code for when females are coded as the reference group. Okay, so there's the women's mean. Okay, there's a 1 unit change, and that translates to a 19.6 unit change on the dependent variable. Okay, and then so the change in y for a 1 unit increase in x. Note that it means the exact same thing it did as when we did continuous regression. It's just now we have a 1 unit span on the dependent variable, and that's it. And so that 1 unit change describes the difference in the group's means. Okay, so the difference between the men's mean and the women's mean. Say we coded them in the opposite way, so men are up here. Now they're coded as a reference group. There's their mean, 78.8. Women are coded as the comparison group over here, 59.2. Okay, now we have a downward slope, but it's the same in absolute value. Okay, so now 19.6, but it's negative because we're going from men to women. Here would be our regression equation for that. Okay, so there's the men's mean. There's our 1 unit change in x, leads to a 19.6 unit decrease, so negative 19.6 is our slope for comparing the mean for women versus men. Okay, so B1, change in y predicted for a 1 unit increase in x. Okay, so difference between women's mean and the men's mean. Okay, so you might be asking, we just talked about the assumptions of regression. So we talked about like how things need to be normally distributed and things like that. So doesn't ordinary least squares require that we assume normality of residuals? Okay, and constant variance. Okay, so yes, it does assume that, but these assumptions are at the levels of the independent variables. So our levels in this case are for men, are say residuals normally distributed for men and at women. So that's the other level. So are they normally distributed for women as well? Okay, so ordinary least squares regression does not require that we make any assumptions about the distribution of the independent variables. So instead of the distribution of the independent variables having to be normal, it's the distribution of the residuals at each level of the dependent variables. So our independent variables can be continuous, normally distributed or not, that's fine. They can be ranks, so people ranking in different class sizes, class ranks or whatever. They can be categorical as well. So that's what we have in this case. Dichotomous, of course, is just a special case of categorical, which we will talk about in just a few minutes. Okay, so here is our data again. So women and men. So women are again coded as the reference group. Okay. So regression only requires that we assume residuals are normal within each level of an independent variable. So here within women and within men. So if we took these scores for women right here and we made a histogram with them, we're assuming that the residuals approximate a normal distribution. So it looks like, that's probably the case here. Certainly doesn't look like, say, all of the they're like a bunch of negative residuals and only a few positive residuals. That doesn't seem to be the case. Same thing for men. So if we took all these points here and we put them in bins and then we computed a histogram, so would that look like a bell-shaped, normally distributed histogram? Okay, and in this case, it does. It doesn't look like it, egregiously violates that assumption. So it only requires that we assume residual variance is constant within each level of an independent variable. So here within women and within men. So what we're basically looking at, is the range of these. So we're looking at residual variance now, not whether they're normally distributed, but just whether residuals, vary more for, men than they do for women. So if you look at the range, the highest residual here and the lowest residual for men here, and compare that to women, it looks like women probably have maybe a little bit of a wider range, but definitely not much. This assumption might be violated if, women had a huge variance, they were all over the map, and men, were very tightly clustered or something like that. Then that assumption might be violated in this case. In that case, you would probably want to do like a non-parametric test. Or like a Welsh t-test or something like that. Okay, so it looks like they are constant. So we haven't violated any of the assumptions of regression in this example, and we could use it just fine. So regression doesn't require the predictor to have any particular distribution. What it talks about is the residual. So those are what the requirements or the assumptions are kind of focused on. Okay, so we don't have this assumption that our predictor actually has to be normally distributed. So that's nice. It's It's nice that we cannot worry about that, and we can still draw conclusions from regression using categorical, or in this case, dichotomous predictors. Okay, so you might also think, shouldn't these data be analyzed using a t-test? So a t-test is kind of our canonical or standard way of comparing two groups. Ever since Student or Gossett, who worked at Guinness Brewing Company, wanted to compare different barley, I think, produce beer. Okay, so that's been what we've been doing. If the independent variable is dichotomous, the dependent variable is continuous, you use a t-test. So why bother with regression? Okay, so when used with a single dichotomous predictor, ordinary least squares regression does produce the exact same results as an independent samples t-test. Okay, so the t-test for B1 in the regression has the same dependent variable t-value and p-value as the independent samples t-test. Okay, so if we actually did regression versus a t-test, okay, so up here is our regression output. Down here is the t-test output. Again, this was originally done in SAS, but you could do it in any program and you should get the same results unless there's something wrong with the program or you entered something wrong. So we can see that we get the same mean values. Okay, so there's our mean value, okay, for the reference group. And then we get the same difference values. So t-tests are focused more on differences, whereas regression is focused more on just coefficients for a model, basically. Okay, so the difference is negative in t-test because it takes the first value minus the second, which really in regression we're taking the second value, whatever is coded as 1, minus the first value, whatever is coded as 0. Okay, our degrees of freedom are the same. Okay, degrees of freedom is 1 for how many degrees of freedom the predictor uses. Okay. And then our t-value is also the same, at least in absolute value. Okay, and then our p-value is going to be the same as well. Okay, so the independent samples t-test can be thought of as a special case of regression. So just like ANOVA can be thought of as a special case of regression. So why should you still use it? The major advantage for using a t-test is just kind of tradition or familiarity. Reviewers and readers who don't know regression will usually know what a t-test is. Hopefully, they at least know what that is. So you might encounter this situation. I know I've encountered it before, where you do a regression and you get a reviewer who doesn't really understand regression very well. Unfortunately, that can happen. And they say, why aren't you just using ANOVA, or why aren't you just using t-test? Really, they're saying that for no other reason than that it's just familiar and it's more common. So why would we want to use regression for a dichotomous predictor? The main thing is flexibility. So really, I would say if you just have this data and that's all you're interested in, you probably want to do a t-test. It's just simpler and more, it's the more common approach. But the regression approach is more flexible. So we could add more predictors to the model, say nuisance predictors. We want to control for socioeconomic status, age, education, other things like that. That's not possible with a t-test. So more on this, of course, in the coming lectures when we expand things a little and look at interactions, particularly between categorical and continuous variables. Okay, so a dummy code allows us to estimate a regression model with a dichotomous predictor. But what if a predictor is categorical, but it has 3 or more categories? Okay, in that case, we use kind of the same method. It just gets a little bit more complicated. So say we have categories or independent variables that are categorical but have multiple values like race or ethnicity, religion, marital status. We've already gone through some examples, using those as different predictors. Okay, so we can still use dummy codes to enter predictors with 3 or more categories. Okay, so when a categorical variable has 3 or more categories, it's entered in a regression using more than one dummy code. Okay, so for the rule is for a variable having G number of categories, we need G minus 1 dummy codes. So in the dichotomous example, G was 2 because we just had 2 categories, and so we just needed 2 minus 1 or 1 dummy code. So we just needed that for 2 categories. For 3 categories, we need 2 dummy codes. Okay, so like those 2 crash test dummies here. So hopefully a lot of you remember crash test dummies. It seems like they've really fallen out. There used to be commercials all the time with crash test dummies, but I guess, they're just not in style right now. Okay, so when we have 3 or more categories, one category is again chosen as the reference group, and it's scored 0 on all dummy codes. Okay, so we choose a reference group as we would with a dichotomous predictor. It involves, a certain degree of subjectivity, but really it's just important to make clear what the reference group is. So what group the reference group is. You always want to state that, like in your methods section or in your results section as you're reporting these results. Always be very clear. Remember that people reading your papers don't have any idea of what your amazing research is about. Okay, so all other categories are scored 1 on one of the dummy codes and then 0 on all others. Okay, so each dummy code only gets a score of 1 for one group. Okay, and so say if we have different religions, maybe religion is our independent variable, our A independent variable that we're looking at. Maybe we have 6 different possibilities. So Buddhist, Christian, Hindu, Jewish, Muslim, and then other or none, all in one, group. Okay, so now we have 6 different categories, or G equals 6. So we need 5 dummy codes. Okay, so we could label these D1 through D5. We could, usually how I like to label these is say I'll pick the reference group. So maybe I'll pick Buddhist as the reference group, and then maybe I'll say I'll create dummy Christian, dummy Hindu, dummy Jewish, dummy Muslim, and dummy other none. So a dummy code, and then I'll declare which category is going to get the 1 in it. So it's going to be coded as 1 by stating that as the name in the dummy code. Okay, that's just something that can help you keep these clear. Okay, so say we're studying Texans, maybe Christianity is the predominant religion in Texas. Okay, so I decide to make that as the reference group. Okay, so Christian is the reference group. It gets a 0 on all dummy codes. Okay, and then maybe D1 is for Buddhist, so I might code it D Buddhist. Just to make it clear to myself, and so the idea would be if you have someone in this that's a Buddhist, you would have like in your Excel sheet or your SPSS sheet or whatever you're using for your data, you would have columns for each of these dummy codes. And then if they were Buddhist, for D1, you would enter 1, and then for all the others, you would enter 0. Okay, if subject 2 was a Christian, then they would get a 0 on all 5 of these dummy codes. Okay, if a participant was Hindu, they would get a 1 for D2. You might label this like D Hindu, and then a 0 for all others. Okay, if a participant was Jewish, they would get a 1 on D3. If a participant was Muslim, they would get a 1 on D4, and then a 0 on all others. And then if a participant said they were anything else, or atheist, or whatever, they would get a 1 on D5, and then a 0 on all others. Okay, so again, what's important here is that these would actually be like 5 columns in your spreadsheet for your data, okay, or however your data is formatted. They would be 5 columns, and then you would enter values on all 5 of them for each participant, okay, based on what they were. Okay, So at the end, I'll pull up a quick Excel spreadsheet to just show kind of, how this can be done pretty easily. And of course, you could also create these in R really easily using if statements and things like that. When we get to multi-level modeling, I'll talk a little bit about a R package called BRMS. What's nice about that is you just have to have one column for your condition, and you declare it as categorical. And then what's nice about that is it computes the dummy codes for you, basically. So it takes your categorical variable, looks at how many levels they are, and then declares one of them as the reference group, and then the others. Or it might actually use effects codes. We'll talk about that when we get to it. Okay, so say we're studying Malaysians. Maybe Islam is the predominant religion there, so we're going to make that the reference group. So if a person in this study was Muslim, they would get 0 on all 5 dummy codes. If they are Buddhist, they get a 1 on D1, 0 on others. Christian, 1 on D2. Hindu, 1 on D3. Jewish, 1 on D4. And then other 1 on D5. Okay, so this would be like a different set of dummy codes you would need to come up with. Okay, so note that each case, so each participant would be assigned values on all of D1 through D5. Okay, so let's look at a 3-category predictor example. Okay, so say we're studying the association between students' college that they're in, so like college as far as section of the university, and their political liberalism versus conservatism. Okay, so maybe we'll have a scale from complete liberal, the donkey over here, to complete conservative, the elephant over here. And so low values would indicate more liberal views, high values indicate more conservative views. So for the sake of simplicity, we'll consider just 3 colleges, so liberal arts. So that's where we are if you're in psychology. Engineering, so I've had some students in, say, industrial engineering before. Business, that would be like what you're in if you're in the business school. Okay, so different colleges. Okay, so there are our colleges. That's going to be our categorical predictor, predicting liberalism versus conservatism. And so we have 3 different groups, so we need 2 dummy codes. Okay, so D1 and D2. So say our reasoning is that engineering is big at Texas A&M. You know, it was started as an agricultural and mechanical school. Lots of people say it's the finest technical school in the South, which I don't mind them saying that. So, say that's the case, we'll make engineering the reference group. Okay, so if someone was in engineering, they would get a code of 0 on each of these. Okay, and then D1 will denote if they're in liberal arts, they'll get a 1 on D1 and a 0 on D2. And if the participant is in business, they'll get a 1 on D2 and a 0 on D1. So here's our regression equation. Okay, so we have the intercept plus B1 times D1 plus B2 times D2. Okay, so we'll have coefficients for each of these dummy codes. So D1 equals 1 for liberal arts, D2 equals 1 for business. So B naught is a predicted value of Y when all predictors D1 and D2 equal 0. Okay, so D1 and D2 equal 0 for the reference group. So if it was the reference group engineering, we would type in, we would have a 0 here for D1 and a 0 here for D2. When we multiply that by the coefficients, it's going to equal 0. So basically, all we're going to be left with is the intercept. Okay, so there are no other predictors in the model. So the predicted score for a group is its mean. Therefore, B naught is the dependent variable mean for the reference group. So for engineering in this case. So this is the same as what B naught, the intercept, meant for our dichotomous example. It was the dependent variable mean for the reference group there as well. Okay. B1 is the change in predicted Y for a 1-unit change in D1, partialing the effect of D2. Okay, so engineering D1 equals 0, liberal arts D1 equals 1. They're 1 unit apart on D1. Business can be ignored because D2's effects are partialed out. Okay, so there are no other predictors in the model, so the predicted score for a group is just its mean. So therefore, B1 is the difference between the dependent variable means for liberal arts versus engineering. Okay, so to say this scale, it's say 100 for complete conservative, 0 for complete liberal, and so it's a 0 to 100 scale for conservatism. And so if B1 is higher, is positive, that would mean that liberal arts students are more conservative than the reference group, engineering students. If B1 is negative, that would mean liberal arts students are more liberal or less conservative than engineering students. Okay, same thing for B2, the change in Y predicted for a 1-unit change in D2. Okay, so that's engineering is coded as 0, business is coded as 1 on D2, so they're 1 unit apart. Okay, no other predictors in the model. Therefore, B2 is a difference between the dependent variable means for business and engineering. Okay, so when a regression model has just a set of dummy codes for one categorical predictor, B0 is the mean of the reference group, and then B1 for each dummy code. Those are the differences between each other group's mean when it's coded as 1 for that dummy code and the reference group's mean. Okay, so B1 was coded as 1 for liberal arts, so it's a difference between, in conservatism, between liberal arts versus engineering. B2 is a difference in conservatism for business versus engineering. Okay, so here are our results. Okay, so from our descriptive statistics that we could compute, we would get means for liberal arts students, engineering, and business. So you can see that on average, it looks like students in engineering and business are a little more conservative than students in liberal arts. So that might be, what you would expect. Okay, so B0 is the engineering mean. So we can see that that comes out as the intercept right here. Okay, so good kind of sanity check that we've kind of seen that computing things in two different ways by just computing the descriptive statistics and then getting them from regression, we come up with the same answer. So this is one way to kind of make sure you're correct, when you're the expert to kind of determine whether you're correct or not. So when there's no one else to ask. So when there's no other expert to ask, which you are getting a PhD, hopefully you're quick on your way to becoming the expert to ask. This is how you verify that you are correct and you've done it correct by doing it multiple different ways and getting the same results. Okay, and then B1 is the liberal arts mean minus the engineering mean. Okay, a difference of 18.02, so lower for liberal arts. Okay, and then business mean is just a little bit higher than engineering mean. We can see for D1 that's significantly different from 0. So liberal arts students on average are less conservative than engineering students. Okay, but then there's no difference or no significant difference between engineering and business students. Okay, so to see if a categorical variable has a significant effect on the dependent variable, we need a test of all dummy codes in the set entered together. Okay, so when there's just one set of dummy codes in the model, this is the F test for R squared for the whole model. So that's just like what we did in this case. Okay, so test whether the set of predictors accounts for significant variance in the dependent variable. Okay, so the set of predictors is the set of dummy codes. Okay, so in other words here, what we're saying is that when we have dummy codes and we look at those actual coefficients, those just tell us like the differences between the means for different groups, like liberal arts versus engineering, business versus engineering. But now this tells us kind of whether there's overall just variance in the mean across our different groups. So this is like looking at the omnibus test for an ANOVA. So overall, are there differences between our groups on political conservatism? Okay, so that's what we're testing here. So we're interested in that as well as like differences between groups. So those comparisons of coefficients, those are really more like our post hoc tests, except we're not doing any of like the corrections or anything like that. We're interpreting it more in a regression framework than in an ANOVA framework. Okay, so when there are other predictors in the model, if we're interested in testing just the effect of that categorical predictor, what we need to do is enter all the other predictors first, and then enter the dummy codes for that categorical predictor in the next step, and then look at this f-test of r-squared change for the dummy code set when it's added to a model with all the other predictors already included. Okay, so the f-test of r-squared change gets the test with the set partialed for all the other predictors in the model. So this is like how we typically partial predictors for each other. Okay, so note that this is not like what we would do for an ANOVA. This is more like what we would do for an ANCOVA. Okay, so we're including all those other predictors first, and then we're looking at what leftover variance is accounted for by this categorical predictor that's represented by the set of dummy codes. Okay, so the tests of the individual dummy codes could also be of interest. So these tell whether particular groups' means differ significantly. Okay, so in many circumstances, only the f-test of the whole set of dummy codes is of interest. Okay, so it tells whether the categorical variable as a whole accounts for significant variance in the dependent variable. Okay, so here college is represented by the dummy codes. Significantly predicts conservatism. So this is just our f-test of the whole model. Since we don't have any other predictors, it's only testing the effect of college. Okay. And then we can look at the individual coefficients. I already did this kind of on the previous slide, but liberal arts students are significantly less conservative than engineering students. Business students do not significantly differ on conservatism from engineering students. Okay, so when our groups is greater than 2, not all possible comparisons between pairs of means are included. So you might have gathered that, well, you know, we did 2 of the 3 possible comparisons, but we did not compare liberal arts to business. Okay, so that's missing in that example. So to get the missing comparisons, we can rerun the regression with a different reference group for the dummy codes. Okay, so here was our original reference group, gives us those comparisons against engineering. Okay, now if we wanted to compare, wanted to use liberal arts as the reference group, we would get this comparison that we were missing. This comparison would be redundant. It's just in the opposite direction of what we've done up here. And then, but we do get a new one, business versus liberal arts. Okay, and then we could do this, but this really wouldn't be getting us anything new than these first 2. Okay, so earlier we looked at several weird alternative coding schemes for a dichotomous predictor. Dummy codes are a better coding scheme because they make regression coefficients more meaningful. Okay, and then there are other coding schemes that also make regression coefficients more meaningful. So we won't talk about these a whole lot, but I want to mention just a few. So dummy codes compare all other groups to a reference group. Effects codes compare all groups except one to the overall mean of the groups. Okay, so in other words here, now when we look at the coefficients, we're going to be asking, the coefficients are essentially telling us how different that group's mean is compared to the overall or grand mean. Okay, so effects codes are really more, getting more similar to what we do when we do an ANOVA basically. Okay, so this is like the grand mean in ANOVA. It's unweighted by group size, so effects codes are also called unweighted effects codes. So just like other coding schemes, dummy codes and effects codes are linear transformations of each other, so they give the same overall model results. So we'll get the same f-tests and r-squared tests, it's just that our coefficients might be different. Okay, so what we do with effects codes is we specify a base group. So a base group, instead of a reference group like what we have in dummy codes. Unlike the reference group, this should be the one of least interest, basically, or at least, this is one idea. The main idea being that we won't be able to make any interpretations based on the coefficient values for the base group, because we won't be able to get those. Okay, so like dummy codes, we need G-1 codes. Score the base group as -1 on all effects codes. Okay, and then all other categories are scored 1 on one of the effects codes and 0 on all others. So this part is just the same as dummy codes, and this part it's just that instead of for the reference group we entered 0, now for the base group for effects codes we enter -1. Okay. So say if we're using religion as our categorical predictor, we have 6 in this example, so we need 5 effects codes. Okay, maybe we label these E1 through E5. You could also label them, something that makes them more clear. Say we're studying people in India. Maybe there's not a very large Jewish population in India, so we reason that we'll make Jewish the base group. Okay, so in that case, if a participant from this study was Jewish, they would get a value of -1 on all 5 effects codes. Okay, if they were Buddhist, they would get 1 for E1, 0 on others, Christian 1 on E2, 0 on others, Hindu 1 on E3, 0 on others, Muslim 1 on E4, 0 on others, and then other 1 on E5, 0 on others. Okay, so codes could be rearranged. We just need to be sure to keep track of which code goes with which group. Okay, so in our other example, predicting liberalism versus conservatism from Students College. Okay, say if we're getting effects codes here, maybe we reason that engineering is big and liberal arts is where psychology is. So we'll make business the base group. So sorry to any business students, but we could also, use a similar reasoning and make the other group as the base group. Okay, so if you're in business and maybe you work with engineers, maybe you'd want to make liberal arts as the base group or something like that. Okay, really it's just important to kind of be clear on which group is the base group. Okay, so that would be what our codes would look like. If someone was in business, they would get -1 for E1 and E2. If they were in liberal arts, they get 1 for E1, 0 on E2, and engineering a 1 on E2 and a 0 on E1. So there would be our regression equation. Okay, so for liberal arts, our predicted value is B0 plus B1 times 1, because we get a 1 for if they're in liberal arts, plus B2 times 0. So this can drop off, leaving us just with B0 plus B1 is our predicted score for liberal arts. Okay, for engineering, okay, so similarly, this B1 times 0 cancels out. It just leaves us with B0 plus B2 for engineering. Okay, so the difference here for effects codes is that B0 will now equal the overall grand mean. Okay, so unweighted grand mean. And then B1 is a difference between that group and then the overall mean. Okay, for business, we could write out the regression equation this way. Okay, so B0 plus B1 times -1 plus B2 times -1, okay, equals B0 minus B1 minus B2. Okay, so there are no other predictors in the model, so these predicted Y values are just the group's means. Okay, so we could compute the predicted mean for business from these coefficients. Okay, so note that say if B1 is negative and B1 is positive, then those could potentially cancel out some. Okay, so those could be of different signs. Okay, so then what is our overall mean? So what is our overall unweighted mean from these coefficients? So we have the liberal arts mean, the engineering mean, and the business mean, and we have them represented by these coefficients. And we know that, say, if we wanted to take the means of all of these groups, we could just add up all of these values and then divide by 3, which is the number that we're adding up. Okay, so we could take a liberal arts mean, engineering mean, and business mean, divide by 3. Since they're represented by these coefficients, we can add them up. Okay, so now what I've done, I got liberal arts mean here, B0 plus B1, engineering mean right here, B0 plus B2, and then business mean right here, B0 minus B1 minus B2. Okay, so I've just translated those into coefficients and then dividing by 3. Okay, I can see that I can further simplify this. So basically this B1, positive B1, cancels out with negative B1 right here. Positive B2 cancels out with negative B2 right here. Okay, and then I'm left with 3 B0. So B0 plus B0 plus B0 equals 3 B0 divided by 3. I can factor out the 3, and I'm left with just B0. Okay, so this is how this coefficient B0, the intercept, now tells us the overall unweighted mean. Okay, so that's just how, we get that from these coefficients. And really, someone thought this clever, math up to where everything kind of aligns. Okay, so therefore B1 is a difference between the liberal arts mean and the overall mean, and B2 is a difference between the engineering mean and the overall mean. Okay. So when a regression model has just a set of effects codes for one categorical predictor, B0 is the overall unweighted mean. Okay, B1 minus B to whatever dummy code you're using, our effects codes you're using, are differences between each other's group's mean. Okay, other than the base group and the overall mean. Okay, so if we look at our example using effects codes, okay, so here's our means for each group, and then the overall mean, we could compute these through like the descriptive statistics commands, okay, or other ways for computing the means. So we get the overall mean right there. Okay, so the overall model results will be the same as what we got from dummy coding. And then B0 is the overall mean, so we can see that it's the same as we got when we computed the overall mean. Okay, and then B1 is the liberal arts mean minus the overall mean. So in other words, the liberal arts students are about 12 units less conservative than the overall mean. Okay, and then E2 is the difference between the engineering mean and the overall mean. So engineers are a little more conservative than the overall mean from these 3 different colleges. Okay, and we could look at the p-values and we could see that that's significantly different than the overall mean. Okay. Okay, so like with dummy codes, you use the f-test of r² to test whether the categorical variable as a whole predicts variance in the dependent variable, and it does in this case. And the individual test of whether group means differ from the overall means may or may not be of interest. So, we might just be interested in the overall grand mean up here and whether there are just differences among our colleges in liberalism versus conservatism. Okay, so you might be thinking, shouldn't these data be analyzed using a one-way ANOVA? Okay, and well, yeah, maybe they should, but sometimes there's more than one correct way to do things. Okay, so we have a categorical independent variable, we have a continuous dependent variable. Why should we bother with regression? Well, when used with a single categorical predictor, regression and ANOVA produce the same results. Okay, the f-test of r² in the regression has the same degrees of freedom and p-value as the f-test of the factor in one-way ANOVA. Okay, so regression, if we look at a regression, here's our F value and P value. If we look at an ANOVA, we get the same value. Okay, same F values and P values. Okay, so everything is the same. So regression was developed separately from t-tests and ANOVA. So they really come from separate traditions, but people in each tradition were doing things correctly, and they got their math straight, and so they came up with the same results basically. Okay, it was only after many years of their development that it was discovered that t-tests and ANOVA were just special cases of regression. Okay, so the regression approach that can be applied to all these methods is called the general linear model. Okay, so you can think of it as a general. So there's a general right here. I'm not sure who that is. That might be Norman Schwarzkopf, but I don't know. But it's a general. There's a line for linear, so the general linear, and then there's a model, so the general linear model. Okay, so interesting interlude. Okay, so in the special case where our sample sizes per group, or n, is equal, ANOVA calculations are simpler than regression calculations. No matrix inversion is required. Okay, so recall that we talked a little bit about matrix inversion and some issues that can come up. Okay, that can hurt matrix inversion. When n per group is unequal and there are two or more categorical predictors, ANOVA calculations are actually impossible. Okay, so one requirement for ANOVA is that our sample size has to be equal. Okay, so what SPSS does is it does a regression and then it presents it as an ANOVA. And that's what other programs would do as well, like JASP or something like that. So why are t-tests and ANOVAs still treated as separate types of analysis? They can be easier to understand than regression. Okay, ANOVA has specialized follow-up tests, so post-hoc tests that aren't typically considered in regression. Okay, so really I think that's easier to understand. It's probably what everyone learns first. That's probably why they're more common. But hopefully, just because it's easier to understand, that doesn't mean it's necessarily better. Hopefully you can also, understand what we're doing with regression, because it's really kind of a broader approach. Okay, they focus more on means than on coefficients. Okay, so ANOVA is focused on comparing means. Regression is focused on coefficients that are in like a model. Okay, so regression is much better for using for actual prediction because you have a predictive model that it's very clear to get predictions for. Okay, and of course, historical inertia is probably a big reason why t-tests and ANOVA are still kind of viewed as separate as regression. I do think that I think more and more we're seeing multi-level models being used in a lot of data sets. So we'll talk about that near the end of the course. But I think that use of multi-level models will kind of make regression and ANOVA seem like more similar and probably lead more people to better understand regression. Okay, so there have been some attempts to unify the presentation of regression and ANOVA. Really, they're just two different ways of looking at the same data sets and really asking the same questions. Okay, so another thing we could do, I think this will be kind of the last thing we touch on. We could add other predictors to the model. So regression models of the categorical predictor can have additional continuous predictors, categorical predictors, or whatever added to the model. Again, the nice thing about regression is its flexibility. We want to add in another predictor that we think we need to control for, or we think interacts with, which we'll talk about next, or we think might have separate effects. We can do that easily with a regression model. Okay, so dummy or effects codes are then partialed for these additional predictors. So in other words, we're looking at unique variance that isn't accounted for by the other predictors in the model. Okay, so dummy codes now describe means adjusted for the other predictors. So these are the same as adjusted means in ANOVA. Okay, so hopefully, more and more you're starting to see kind of the connection between regression and ANOVA, with ANOVA kind of being, say, a bridge or a link between the two. So say in our example, we add parents' political beliefs as a predictor to the dummy coded model. So here's our regression equation. Okay, D1 for liberal arts, D2 for business, and then X1 for parents' beliefs. So maybe that's continuous valued from 0 to 100, 0 completely liberal, 100 completely conservative. Okay, so whatever their parents' beliefs. Okay, so B naught is Y predicted when all predictors are 0. Okay, so B naught is a predicted conservatism for students in engineering whose parents score 0 on conservatism. Okay, so note that we could make this a more meaningful value by centering parents' beliefs. Okay, so that's probably a good idea in this case, is to center parents' beliefs, if we were doing something like this, or we had a data set like this. Okay, so B1 is the change in Y predicted for a 1 unit change in D1, partially the effects of D2 and X1. Okay, and then B1 is a difference between liberal arts mean and engineering mean, holding parents' beliefs constant. Okay, or adjusting for the difference in their beliefs. Okay, so B2, again, it's the same thing, 1 unit change in D1, or the difference between the business mean and the engineering mean, holding parents' beliefs constant, okay, or adjusting for the differences in their beliefs. Okay, and then B3 is the change in Y predicted for a 1 unit change in X1, partialing the effects of D1 and D2. Okay, so this is just like how we were interpreting continuous variables in the first half of the course. So it's a predicted change in conservatism for a 1 unit change in parents' beliefs, holding college constants. Okay, so the same interpretation X1 would have if the other variable in the model were continuous. Okay. So there's our engineering mean for parents scoring 0. So we didn't center in this case. Okay, difference between adjusted liberal arts and adjusted engineering means still significant after we've accounted for parents' beliefs. Okay, difference between adjusted business and adjusted engineering means. Okay, and then effect of parents' beliefs controlling for college. Okay, so we can see that that was significant, and then parents' beliefs is correlated with their kids' beliefs. Okay, so positively correlated. So that's something that I think has been shown. Parents' beliefs tend to be correlated with their kids' beliefs to some degree at least. Okay, so now that the categorical predictor isn't the only predictor in the model, we have to use the f-test of r-squared change for the dummy codes to test whether college is a significant predictor. Okay, so what we're going to do is first enter parents' beliefs as a predictor in the first step, and then in the second step, we're going to enter the dummy codes for college, and then look at that f-test of r-squared change from the first step to the second step, and that'll tell us the variance accounted for college after accounting for the variance for parents' beliefs. Okay. So college is a significant predictor even with parents' beliefs in the model. So that's just our f-test for r-squared change. Okay. So when categorical predictors are entered in model using codes, the code should be included or excluded from the model as a set. Okay, so the idea here is you just have one variable, but we have to have multiple codes for that variable. So we just treat those codes for that variable as a set, and we enter or remove them as a set. Okay, so if we, for example, dropped one code from the model while retaining the others, this would change the meaning of the remaining codes. Okay, so we wouldn't want to do that. Okay, so these are the dummy codes for the example. So engineering coded as 0. Okay, D1 compares liberal arts against engineering. D2 compares business against engineering. Now say we drop D2 from the model. Okay, now what we're doing is we're going to compare liberal arts against engineering and business together. Okay, so D1 is no longer partialed for D2. Okay, so in other words, we could do that if we wanted to, but this would be like conflating engineering and business together. So maybe, there could be a reason why you want to do that, but if you are going to do that, you should, have a reason for doing so, and you should explain that in your paper. Okay, so this changes the meaning of the categorical variable. Engineering and business are combined. Okay, so note that, again, like I was just saying, it's perfectly okay to collapse groups and categorical variables intentionally. Okay, so for example, if we plan to use 5 race ethnicity categories, but 97% of participants fell into 3 of them, we might combine the other 2 and call it other. Okay, we could have a simple, another example, say with gender. If maybe most people identify as male or female, but some identify as another gender. If we don't have enough, we might just lump everyone else into other and call it that. Of course, there could be subjective reasons for doing that or not based on, the literature in a particular field. Okay, so we only need to be aware of unintentionally collapsing categories by removing code variables from a model individually. Okay, so when we, one note on standardizing, so when we enter categorical variables using dummy or effects codes, we do not want to look at standardized regression results. Okay, so standardization makes coefficients easy to interpret by giving all predictors a common metric. Okay, so the standard deviation. But with dummy or effects codes, we've already kind of set everything up so it's easy to interpret the results. So we already have interpretable metrics. Standardization would completely ruin that. So in other words, when you look at the coefficients, don't look at the standardized results for categorical predictors. Look at the unstandardized coefficients because we already have things in a way that's easy to interpret the coefficients. Okay, some other coding schemes, weighted effects codes, so like regular unweighted effects codes, except they use weighted means. Okay, so use when our sample sizes per group, our n's, are different, and the differences are important. This is probably, kind of unusual, but it could be the case. Contrast codes are also possible. So I use contrast codes a lot for like multi-level modeling. This would be like you code one group as -1, the other group as 1. So we talked about contrast codes some when we set up our own contrast. Use a set of orthogonal contrasts to enter the categorical predictor. And contrast codes, I think, are probably what you would want to use to have your results most completely line up with ANOVA results. Okay, so contrasts are chosen to test hypotheses of interest, just like we would do contrasts in ANOVA. Okay. So here's the syntax for SPSS. I don't have any R or JASP examples for this lecture, but we'll be doing some for our interactions. So categorical predictors in SPSS. So this is just saying if it's business, D1 equals 0, D2 equals 1. If it's engineering, both dummy codes equal 0. If it's liberal arts, both dummy codes equals 1. Note that if you're proficient in R, or hopefully you're gaining proficiency in R, you can also use if statements in R to do something like this. Okay. So this syntax allows us to assign multiple dummy codes to each group of a categorical variable. Okay, so if then else structure means that only one group of commands is processed. Okay, so assign people in business, D1, same thing, we've already done that. Okay, it's all pretty simple. So that syntax just made the dummy codes and assigned them for each group. So this could be done just as easily or easier using, say, a spreadsheet editor. Create dummy code variables and assign the appropriate 0 or 1 for each case, depending on what group it is in. Okay, after that, you can use the same point and click regression commands. If you're working in R, then you can use mutate command to create new variables. Like I mentioned in a previous lecture, you can also use the money sign after a data set, after a data frame's been declared, to declare a new variable from old variables. So real quick, I'll just show you how to do this in, say, Excel. So say this is an Excel spreadsheet. Maybe I'll try to enlarge this a little. Okay. So say this is an Excel spreadsheet. I have different colleges, LA, Eng, or bus for each one. And then I have dummy codes 1 and 2. So if I wanted to do this in Excel to type a formula, what I could do is say I want to set, well, let's do engineering as the reference group. So if this equals, so LA is going to be 1 for D1. Okay, so that equals, I'll type in quotes LA. Okay, then it's going to be 1, else 0. Okay, so that's the value of false. Okay, and so I type that in. Okay, and then dummy code 2 is going to be for business, so I'll do the same if statement. Okay, if this right here, this column equals bus, so I need it's text, so I need to put it in quotes. If it was just a number, I wouldn't need the quotes. Okay, so bus for business, then it's 1, else it's 0. Okay, and so now in Excel I've done that. Okay, and so I've done those formulas, and it's going to reference whatever is in column B in the same row. Okay, so if I do that and then I highlight and drag this bottom right edge, okay, I can see that it'll copy these formulas. So now I've done the dummy codes already, basically. So I got engineering gives us zeros for both, liberal arts 1 for D1, business 1 for D2. Okay, and so you can see in the formula up here, like what formula is in each cell. Okay, so that's a quick kind of example of how to type these formulas in Excel. And then, if you wanted to do this in Excel, you could save it as a .csv file, because I have my header row up here. And then I could open it like directly in JASP if I wanted to. Okay, so let's go back to my, where's my PowerPoint? Okay, so let's go back to this. We're almost done here. Sorry, this is getting long. Okay, yeah, so here's the syntax for SPSS. This was the first model, just predicting liberal conservative from our dummy codes. And then down here is our second model, the hierarchical model. So we tell it to enter parents, so that's their beliefs first, and then enter the dummy codes in the second step. So this will give us, and then for statistics, we've specified change, that we want R squared change. Okay, and so here is our results. Okay, so this is for the first model. This is all stuff we've seen before. Okay, so there's the intercept, the mean for engineering, difference between engineering and liberal arts, difference between engineering and business. Okay, and then this is for the second model where we entered parents first. Okay, and then we got that. So unlike when we're actually doing hierarchical regression, we want to take all results from the last model, but we're just using hierarchical regression to get SPSS to do the f-test of R squared change. Okay, so yeah, that'll be on the next slide. So we would use this for like the coefficients, because we want parents to be partialed out, or we want to look at parents after partialing out the effect of college. Okay, and so we get that. These are dummy codes after accounting for parents' political beliefs. Okay, so you can note that this was only, I think, like a 0.68 difference between business and engineering for D2. Now it's a little larger after accounting for parents' beliefs, but that type of thing can happen. Okay, and then finally we get the f-test of r-squared change. So for step 2, we can look at step 1. We can see that parents' beliefs is significant just on its own. And then for step 2, we can look at our r-squared change for that. And then we can see that that is significant, 2 degrees of freedom, because we had 2 dummy code predictors. Okay, and so we could see that as a set, after partialing out for parents' beliefs, college is still a significant predictor. Okay, so that's what we want. And then that is the end of this lecture. And so next, I believe we'll start talking about interaction. So thanks for listening, and then feel free to email me or add questions in the text chat that I sent out if you have questions. So hopefully this was informative, and you now have an understanding of how we treat categorical predictors. All right, that's it for today.